All right, so welcome to my presentation about Beyond STM. STM is the simple TCP messaging library that NI has released. It's on VIPM, and we're going to talk about why I have a whole bunch of other stuff that may or not be helpful to you. Hopefully it is, but provides a couple more features. So who am I? Too far. So I'm Derrick Bommarito. You can find me on GitHub and VIPM as Illuminated-G is the moniker I do most of my open source LabVIEW development on. Right now, I'm a senior technical support engineer at NI. Here, I'm presenting from the office this evening. So if you submit a case for LabVIEW, test stand, RT, FPGA, web, DAC, DSA, and a handful of other things, there's probably a good chance I will know about it and maybe help out with it. Prior to working here at NI, I was a systems integrator and alliance partner for 8 years. I've done everything from high pressure engineering testing to medical device validation to aircraft chassis sensor simulation. So a smattering of a whole bunch of random stuff, whatever our business development guy could drum up for us. My main focus is on LabVIEW development and software architecture, which you can see with all the packages I like to write and practice my API development and design skills. And as a hobby, I love poking at the dark corners of LabVIEW. The edge use cases of the edge use cases, stuff that I am told would never get fixed if I ever find a bug in it, except that it did, like when I tried using Xnode with channels together. Sorry for the duplicate intro. I definitely copied and pasted that from my earlier presentation. So simple TCP messaging, NI has it published on VIPM, and it makes messaging easy. And for this presentation, we're going to talk about messaging as the ability to interleave different data types, different messages over a single TCP connection. So you can attach an ID string to it and some arbitrary data. Maybe it's an array of waveforms, maybe it's some control state cluster, whatever those different situations might be that you're going to send to a connected endpoint. Now, with the STM module library, all the message IDs need to be defined up front, which makes it really performant because it can just send the numerical index of what the registered message IDs are. So it's going to send 1 byte, whereas my libraries actually send the string value. And so that means the STM is going to be, need less bandwidth, but at the scope of the messages we're talking about, usually that's going to be a relatively low proportion of the message. But it does not, STM does not make TCP easy. You still have to do the TCP management yourself. And so you have to set up the server, the listener, accept connections. Once you have a TCP connection, you can then register that with the STM library and start using that with messaging. So quick TCP recap. So most of the issues that I've come across while I've been working here at NI in the support organization, people have trouble with the LabVIEW TCP primitives because they just don't understand TCP. So I want to take a minute and we'll talk about TCP itself, regardless of how it's being used, whether you're using it in LabVIEW or any other language. So TCP listeners, which we typically call the server, they'll listen on a specified port, and that's where clients will connect to that support you're specifying anytime you're specifying, what remote system to connect to. But then, however, once a client connects, it gets its own different port that it actually does the communication on. And that way, the listening port is still the port that new clients can connect to. And then they come in, they get their own port, and that's the port that the communication actually happens on. It's kind of like at a hotel. You go in, you go to the front desk. That's like the server listening port. You get your room to go to, and then when you call DoorDash and get a food delivery, they're going to bring it to you. They can bring it right to your door. They don't have to go to the front desk and then up to you. The listener, the server listening port, continues to accept new connections until it's closed. So in LabVIEW's case, and I've got the screenshot of the context help up there in the corner, there's two TCP connection refs that are passed out of that node. There's the listener ID out because that is still the listener port. That's only the port is only used to accept connections. And then the one you're actually interested in for communicating with is the connection ID that comes out of the bottom. And then once that connection ID is created, it's got its own lifetime. You can close down the listener and the client connection persists and can continue to communicate. We'll briefly talk about TLS Overview. All of my libraries that do TCP do support TLS. So the small library I'm going to talk about, the larger library I'm going to talk about, and WebSockets all support TLS since that's been added in LabVIEW 2020. I think they showed up in, I forget exactly what year. But there's two verbs we're going to talk about, accepts and starts. The server accepts a connection. The client starts the connection, and the server has a private key and then a certificate chain. As part of the TLS handshake, that server is going to send that certificate to the client, and the client is going to validate a couple things about that certificate. It's going to validate the name that the server identifies itself with in that certificate. And one of the things we'll look at is why there is a separate host name field that gets used with the TLS functions when you might have already used a host name with the TCP open reference, but they're two separate things. One is only for getting the IP address to connect to with TCP. The other one is for that certificate name matching. So two roads diverged in a yellow wood. So I'm going to be talking about two sets of libraries. Well, I'm going to be talking about a single package and then a whole family of packages. One of them is tiny, does point-to-point, so it's just a single client and a single server. Once that server accepts a connection from a client, it stops listening for new connections until that client disconnects. Messaging is optional. If you want to use it just for the connection management and you're only ever going to be using the same data type that you send to the remote endpoint, you don't have to use the the message ID field. You do reads and writes directly on the connection. It doesn't use OOP at all. It is just a DVR wrapped cluster, so you can branch it and read and write in multiple locations. You wouldn't want to read in multiple locations, but you can write to it from multiple locations. And internally, it just uses LabVIEW's flattened to string. So it's pretty performant, but it does have to be compatible with the flattened to string for any data types you use. And then there's the whole streams family of packages. They're not tiny. There's a bunch of them, and none of them are small. They do pretty much all support anytime there is a client server involved with them. The server will accept multiple client connections. Messaging is separated out into its own package, and it can work on multiple stream types. And we'll look at an example where I'm using one messaging API with both TCP connections to other LabVIEW programs and WebSocket connections to web pages. It uses VI callbacks, so you're not directly reading data from a stream or anything. You're registering callbacks, so they're going to get called when the messaging API receives a message with an ID. It is class-based. You don't have to be your program doesn't have to be class-based to use these libraries, but the libraries themselves are class-based. It doesn't, even though it's class-based, it doesn't have a message class that you override to make new message types. There's just the message class that abstracts how you can get data in and out of messages. And it can support multiple formats. Right now, it does support the same flattened to string that the tiny TCP does, but it can also do JSON formatting for any data type that the flattened and unflattened JSON nodes work with. So here is a block. Here's an example that we'll be looking at for the tiny TCP library. It's already out of date, and we'll take a look at what the actual one looks like in a couple minutes. But it is pretty small. So on the front panel, really simple functionality. If we look at the block diagram actually first, we can see here that we're going to initialize a connection, if I can remember my zoom in shortcuts. We're going to initialize a connection, and then you can use it. You write messages to it, and you can read messages from it. Check to see if it stopped. We're not going to look at this one because you don't need to do this anymore. This is a change I made earlier today. But pretty straightforward to use. There's some utility VIs for getting the current state, whether something's connected or not. This VI here is for whether or not the connection has been shut down. And then there's a couple of other utility VIs for opening it, closing it, control like that. One of the features of the tiny TCP library is that it allows using enumerations for the message ID. So you don't have to worry about typos or making sure that you copy and paste string values all over the place. It will automatically flatten the enumeration string value for you if you wire that in. It is initially specified by a string, but you can use enumerations as a convenience. Anything else I need to talk about here? I think that's it. So this demo that we'll be looking at in a bit, there is a server application. So it's got two sliders that it can send to the client, and then the client has two sliders that it can send back. One of the things is, so we'll be able to see it if we look closer down here, is slider D is a signed 8-bit integer, and slider A is an I32. One of them is a double, one of them is a U32. So this demonstrates how you can flexibly change what data types you're using with it. The typical use case would be is you figure out what the message ID is. So if you're using an enumeration, you tell it what the enumeration is that it should try to convert the string from. And then you can use a case structure. Once you know what message it is, you know what data type it is, so you can use your unflattened from string to get the correct data type. And it doesn't have to be basic data types. You can use arrays, clusters, anything that will work with the flattened and unflattened from string. And it does also support TLS, as I said. So on the server, you'd specify that private key, the path to the private key, the path to the private key's signing chain. If your private key is password protected, you would enter the password. This is actually also extra now. I'm getting all my keystrokes messed up here. So you don't need to explicitly enable it. As long as you're sending in the value, it knows you're trying to enable it. And then on the client side, if you are using a self-signed certificate or a certificate that's not from a trusted certificate signing authority, you just have to specify the certificate chain. Alternatively, if it is something that's going to be trusted by the operating system, you could just use operating system certificates, and you'd use the built-in ones. But these TLS configurations are optional inputs on the connection initialization routines. So pretty straightforward to define the configuration up front. And then anytime it connects, it'll do the TLS handshake for you, and your data will all be encrypted. So this is the web of the libraries that are involved with these stream packages, with one extra hangout over here with a UI library I've got on VIPM.
I love you, Derrick.
Hi, Norm. And this is what is out there on VIPM. If you are looking specifically for WebSockets or TCP, all the dependencies are set up. So you can just look for the type of communication you're trying to do, and you'll get all the appropriate dependencies. I am going to save this stuff for the end. If anybody does have questions about how it's architected, we can dive into this into more detail if anybody actually cares. I'm going to slide through these relatively quickly. So as I mentioned, one of the things that the streams libraries use is a VI callback mechanism. So this is just you register a VI reference, and we can see here on the right block diagram here where we're using a VI reference and a call by reference node, just so external code applications can register what code to run to handle messages, connection events, disconnection events, and so that's how it's reusable and has the pluggable behavior is via those VI callbacks. So there's a handful of classes in this scheme in these packages that do the TCP stuff. If you do want to use them directly, one of the features it does have is it can automatically prepend lengths for you. And when you're reading data back, you can tell it to look for that prepended length. You don't have to worry about specific message formats or anything like that. Makes it a little simpler in that case. This does launch a bunch of stuff in the background asynchronously. If you saw my presentation this morning talking about reference lifetimes in LabVIEW, that may impact you if you're unfamiliar with that. This does not use interfaces anywhere. Where interfaces would be useful in an architecture like this is for the message handlers. If you wanted to register some code to accept messages, that could be done with interfaces, but I don't like the class count explosion that can lead to. If you do have the option of having a single handler can handle multiple message IDs. It would just look at what is the message ID inside of itself, and then also, have its own case structure to decide what to do with the different messages. And yeah, you could do that with interfaces, and then any class could become, a message handler. But I tend to prefer the callback mechanism because it doesn't enforce, needing to make different handler classes. And just a little bit more flexible. It's pretty much how I accomplished interfaces before interfaces existed. So messaging, again, messaging runs in an asynchronous VI for the message reading. You do just tell it to send messages directly. You can send messages to specific endpoints if you kept track of specific endpoints. Messages do have a utility to where you can reply to the specific sender of a message. So, again, these are all meant to support multiple clients connecting to a server. So if you're on the server and somebody, when they first connect, sends a message that says, hey, give me my initial state, you build that initial state and you use the reply method that's on the message class to make that super easy. And you just send the data right back to the person that asked for it. This is what registering message callbacks look like. You give them an ID. So you create the message handler, then you can register callbacks with the message handler, the message manager. Sorry. This library does not do that trick where it automatically flattens enumerations. I made my own little type conversion looking VI to do that. I will probably eventually add that same functionality to here, although it does require more VIs to become malleable VIs, which is sometimes treading on shaky ground. But so, for instance, with this, anytime the user info message is received, it would send whatever the data payload is with that into the user info callback, which could then unflatten it properly and do whatever it needed to do with that data. The other callback type you can register is a connection callback. So if you want to know when something initially connects, you can then immediately send it data. It doesn't have to ask for it, and then you reply. You could just go, oh, there's a new client that connected. Send them the initial state. And it also is triggered for disconnects. So if you needed some kind of like e-stop behavior for if the network goes out or the system hangs, whatever would cause the the underlying connection, whether it's TCP or WebSockets, to go down, you could react to that somehow if you need it. And then finally, using it with one of the streaming-based endpoints is you create your TCP server, TCP client, WebSocket server, WebSocket client. You could use this with serial streams if you wanted to. You create those, and then you just tell the messaging manager, here's an endpoint type for you to use, and then it'll use it for you. So I do have a couple of planned features. I do want to make GWeb libraries for automatic flattening and structuring of the JSON messages that you would use from GWeb to make talking to LabVIEW applications that are using the messaging API, make it really easy to get data back and forth with those. Also a JavaScript library. Right now I do have JavaScript code written, but it's specific to the examples that I've written. It's pretty small, but there certainly could be a nice, it's real nice when you can just pull in a JavaScript file and use it. I do want to provide a simplified TCP TLS config like the Tiny TCP has and what WebSockets has. Right now with the TCP stream, there are accept and start methods that you have to explicitly call. And I do want to make some automated tooling for callback creation. Right now you have to make a VI, copy the front panel from one of the libraries for the correct connector pane layout and kind of do some of that yourself. So eventually I'd like to automate that. And then any issues you guys can submit to the GitHub. As always, this stuff is on my GitHub. If you go to my publisher page, which I will have a link to here shortly, you can find links to the repositories. It's either listed as the repository or the homepage, and you can submit issues if you have any feature requests or anything like that. So before we get into watching some of this run, there's the link to my publisher page on VIPM.io. And does anybody have any questions yet? All right, so first, the Tiny TCP demo. So I've got two demos here. They're the ones I showed in the slides. That's not what I wanted to click. My hand-eye coordination is getting a little fuzzy. So we run these VIs. They start off in the idle state. You can open the both of them, and now I can start sending the values back and forth. As I said, there was an extra VI that needed to be running at the bottom, but now I've simplified that. That does launch asynchronously. I got it to shut down robustly. So you can't just double click on it to open it, but generally you shouldn't need to. It's just a very simple state machine. But again, pretty simple. You initialize it. You can open it or close it, read from it. Pretty straightforward on this demo. You can close and reopen, and it connects again immediately. That is actually different from the stream-based implementations. And then the TLS client and server, I'm not going to bother running these. These are very nearly identical. They have the TLS configuration applied. Again, I cleaned up some of the extra fields that aren't necessary because, of course, the code knows if you specified a value for some of the other fields, you're obviously trying to enable that feature. So just cleaned up some of the extra little bits. These all do have palettes. So when you install these packages, you will get an Illuminated-G palette, which you can get the Tiny TCP. There's all the functions and some of the controls you would need to use. And as we'll see, the stream-based stuff can expand out a bit more. But everything does have palettes made. I don't know if they're the most organized, but there's some method to the madness when I created the palettes. They do, most of them, install examples that go into the LabVIEW examples folder. So you'd be able to take a look at those or click the examples button in the package info. Unfortunately for me right now, VIPM is overloading this virtual machine, so I can't show that. Any questions on the tiny TCP before I move on? It's always fun trying to figure out what the delay is on a on a stream and give enough time, but not too much. All right, we're gonna move on. So next up, we're gonna look at just the base TCP connection. So this is going to be a little bit of a chat application example. So I've run the server UI popped up over here, and now I can run clients, and it is going to allow me to create multiple ones of these. So we can see the connected clients updated over here. If I run this again, I can get another one. They're both connected to the server. You can send the chats back and forth. And everything works nice and clean, shuts down cleanly. I have run Desktop Execution Trace Toolkit on this. So I have done my homework on these libraries. The applications themselves are relatively small for what they have in them. So this is the entire, I'm going to call it the user code for the chat. There are connection callbacks, and then these are directly doing reads and writes to the TCP stream. So for instance, if we look at the server UI, it will, so here, so this is a sub VI of the chat server class application class. So the server gets passed in at this point. The TCP server is already connected or initiated, and as they connect, the class keeps track of the connected clients. So for all of the ones that are connected, we'll iterate over them, see if any of them have sent a message, and then if they have, I'm going to switch over to live. It will then iterate over all the other clients and forward the message to them. So pretty straightforward implementation here, just to get different clients to be able to send messages through a central server. But the key takeaway with this is this isn't using the messaging API. This is directly doing reads and writes on the underlying TCP stream. How do I get out of live screen? Okay, there we go. Any questions on the TCP stream? So now we're going to move up to, wait, do I have a WebSockets example? I've got that WebSocket. Now that is the WebSockets example to show off. So I do have, once we get to the messaging API layer, minimize. Same concept. We got a server that we can launch. Now it's a little bit fancier just because this is a bigger demo. I took more time with this demo. And again, we can create multiple clients. So I'm just going to go ahead and get 3 clients made. Close the launcher. So we'll connect up the first one. This one is a little bit different. It actually asks you to specify the host name. So we'll specify the host name. And of course, it's going to break. Why is it broken? Did I typo localhost? Let's try the IP address. Okay, I must have typoed localhost. I'm sure somebody might have been screaming that at the presentation screen. Okay, so assuming you know how to spell localhost, it connects, then prompts the user to enter a username. So let's try this again. Yep, works great when you make sure you don't type it. Now, this demo does actually check for the username, and it'll prompt you again if you're trying to use the username that's already taken. This is a little bit fancier. You can turn timestamps on and off, but this goes through and demonstrates the messaging API. So if you want to look at how can you do client-server applications, you're going to want to look at this streams messaging example, which is its own package, because it glues together the messaging, which doesn't directly depend on TCP. Messaging can work with any of the stream implementations, and then the TCP stream implementation. But these can, of course, send the messages. You can click it, see what time they connected, what their connection information was, boot them off the server. This one was the one that was GLA Summit got kicked. Close them all down, everything shuts down. IV's not going to complain about any VIs running in the background. Hooray. And then here is, we'll actually look at this code because this isn't super huge. This is how small a message-based application can be. So the first thing this demo does is that, let's actually look at what it does first. That'd probably be helpful. So if I run the client, run the server, I can change the slider on the server, and we see it update on the client. Also, the server is sending its loops iteration count to the client, and so we can see that updating here. And I can stop those. And this also does allow doing JSON formatting. So if I were to look at this in something like Wireshark, we would see that the values that the server are sending. So this is the, let me go ahead and get rid of that for now. So this is the server application. So it is doing a message broadcast with these message IDs. So this is just string values. This, of course, is the first one. The iteration is an I32, and the slider value is a double. So when you first create when you register an underlying stream type endpoint with a messaging manager, you can tell what format you want it to use. By default, it's going to use LabVIEW binary, which is just the flattened and unflattened string. But you can also specify JSON as an additional option. So if you needed to talk to something else that's expecting JSON formatted data, or the WebSocket library works really well with JSON formatted data, since that's typically going to be running in a web browser, which can do JSON stringify and parsing. So that just makes that really convenient to work with. So pretty straightforward. We're going to turn an indicator on as long as the messaging manager knows that there's a client connected. And we're just going to, 10 times a second, send over these two values. This is the receiving side. So again, we're going to set up the TCP client first. First, we're going to store some UI references in a functional global, just because I wanted to be lazy and just use a functional global to grab the references to be updated from the message callbacks. But we're going to create the TCP client. All of the streaming endpoints do use URIs to identify themselves and or the remote system that they're connecting to. So that's why on the server it was a 0.0.0.0, and then the port number to listen on. And the client, you specify the host name or IP and the port name to use. So again, we're going to create that, tell it to use whatever format was specified on the front panel, register the message callbacks to use. So just discussed before, these are going to be the VIs that get called when messages with these IDs are received. And then that's all this needs to do until the user stops the application. For an example of what one of these look like, so we can see a little bit of the messaging, the message class and what it provides. So it also has a malleable VI that just saves a little bit of work in unflattening the data correctly. The other nice thing is when you do use the built-in unflattening is you don't have to care if the underlying format was JSON, LabVIEW, or anything that gets added in the future. That is stored in this message class. So it's all hidden under the hood. You just tell it, hey, we're expecting this message to contain a double value. You get that out. If you did have a message handler that was handling multiple messages, there is an access through on the message to get what the message ID was. You'd have your case structure, and then you could use the appropriate read data. So just saving some extra work of having to drop down your own formatting and your own format handling. It's all baked right into the API. And now getting to a real neat demo. I seem to have closed a VI on accident. That's all right. Where was it? It was over here. So if you saw my presentation at GDevCon or have heard about it, I did write an entire web server that I used for an internal project here at NI in LabVIEW. Uses all of the native TCP functionality in LabVIEW, and it can serve as an alternative to web services. It follows a whole processing flow, and you can look at the details on the GitHub repository if you want. But this is, I finally finished the functionality for the web server being able to accept WebSocket connections in addition to page requests. So once I run this server, I'm going to open up the browser, and this is listening on port 36987. So if I type L, it's going to autocomplete because of all the times I've tested this. So this is just a simple web page with some JavaScript running to do the WebSocket connection and then accept messages to update the UI, as well as send whatever value is in this input to the server so we can see what the last received greeting message was, and these values match here. If I hit refresh traces, here was the initial page request. It just responded with a normal HTTP response with the page content. And then here's where it actually accessed the WebSocket resource, and it responded with a WebSocket upgrade request. So this HTTP server has a whole bunch of debugging, logging built into it. You can see how long it takes to do some of the processing and communication. Configuring it's relatively straightforward. You initialize the server, tell the server you want a WebSocket to listen at this specific path. Anytime a WebSocket connection request comes in on that path, it'll come in on the WebSocket server that it creates with that. You can register that with the messaging API and then do everything with messages. And that runs nearly identically to this example that we're looking at. So this is going to probably be the least impressive functionality with hopefully pretty impressive outcome. So this is a really fancy stopwatch. So you can do all the things you'd expect to be able to do with a stopwatch. You can start it, you can reset it to 0, you can pause it, resume it, pause it, reset it to 0. You can also run LabVIEW-based clients. So again, I'm going to specify the server address, the port that the server is listening on. And I now have this LabVIEW UI where I can do all of the same stuff. Doesn't matter, all of these actions that are getting commanded are being sent to the server. The server's doing all the actual state management and just publishing out the timer value and state. So there's very little logic in this client, but I can do this as many times as I want and work on any one of the interfaces. And then I can also bring up Chrome again. Oh boy, I might be overloading my computer just a little bit. This one, the HTTP requests are listening on 7080. This isn't using the web server. This is just using a TCP connection to read the request and just send a canned response. But now I've got a web page that is showing the timer. And it can also do all of the stuff. And I can open multiple copies of this. So this is video. If you are connected to me on LinkedIn at all, you've seen this example. But now I can... Why is that one not working? I broke something. This one's not sending messages for some reason. All right. Yay, live demos. All these other ones are working. Just this one is being uncooperative. Oh, yeah, it's just running slow for some reason. All right, looks like I have introduced a bug somewhere. I will have to track that down. So if we look at, go ahead and close all these down. We don't need to look at that. This is a little application I've encapsulated in a class. At first, we're just initializing the TCP connection that is going to accept and respond to the page request. And then initializing the message API. So this is a little bit more complex than before, but not really. So I've got the top half is the messaging API, and the bottom half is for the different stream endpoints. So this is the main thing I want to demonstrate here is that the messaging API, again, doesn't care what the underlying stream type is. And in fact, we're here combining a WebSocket server and a TCP server. Now, we are specifying different formats for them. The flattened to string is more efficient for LabVIEW to do than to do JSON formatting. So where we can, such as other LabVIEW programs that do use the TCP connection, we'll use the LabVIEW binary format, flattened string format. Whereas anything that connects with the WebSocket will get the JSON formatting. Here we're, just like before, we're registering some message handlers. In this case, we're using one message handler to handle 3 different message IDs. So this is, anytime a remote client sends a start, pause, or reset command, it is getting handled by this message handler. And then, of course, the endpoints are getting set up down here, and that is getting drawn funky. But yeah, so pretty similar to what you've seen before, other than these bits right here. These are in this box. These are the only bits of this application that know or care about the fact that there's WebSockets and TCP. From outside of this red box that I've drawn, everything else is identical code. Nowhere else cares whether it's TCP or WebSockets. which is the nice thing, I think, about this library. It might be a little biased. For instance, this is where the timer value is being sent. So all the timer details are hidden in this server class. It's pretty much exactly what you would want to implement in your CLD in whatever format you're wanting to do. But it does all the stuff that a CLD timer should do, like a stopwatch. And it's just returning the value already formatted as a string, and we can just broadcast that out to any connected clients with the messaging API, just with the timer value as the message ID. Again, doesn't care what the format is, doesn't care what type the underlying stream is. All of that is hidden underneath. And then just displaying what the expected URL is to make it easy to pull it up. And then for the serving the page is really simple as far as this code goes. Also on VIPM, I've got some HTTP utilities, which are useful for doing HTTP server parsing and response generation, whereas all of the other HTTP APIs and libraries that exist are generally for when you want to be an HTTP client and request data from other systems. So, for instance, one of these will read an HTTP request from just a TCP reference. We don't actually check it for validity other than it didn't produce an error parsing the HTTP. We don't care what page requested or anything like that was. We got a valid HTTP request. We're going to respond with that page content that had the buttons and the value displays and the state display. So that is what I think is the cool demo, getting to mix and match LabVIEW clients, WebSocket clients, and as long as you're using the messaging API, you get to ignore many of the formatting and streaming connection details. I was going to have a demo where I show using the serial stream in a virtual terminal emulator that I've written in LabVIEW, but I forgot to bring my Raspberry Pi Pico with me, so I do not have something that I can easily connect to with serial and demo that. But maybe I'll just save that for another presentation sometime. So that is the end of the demos for these libraries. What questions did anybody have? Andrew, did you get your questions answered about the hierarchy? Is there anything specific you'd like to look at? Any trades I went through in composition. What do you mean by that? While he's responding, so for instance, here is one of the package details page on VIPM.io, and the homepage link will bring you to the GitHub repository. So if there's any feedback or questions or issues you find, definitely feel free to hit up the issues page on GitHub. Why is this Oh boy, it's stuck. There we go. The fun of I've got Zoomit installed on my host OS and Zoomit installed on the guest OS to make it work, and sometimes they fight each other. So yeah, don't be shy about using the issues tabs on these repositories. Feel free to ask any questions or point out issues you come across. Did I have a guide for separating top object tree branches? Okay, so let's look at class hierarchy. Got other projects open, so hopefully this doesn't get too polluted. Maybe someday it'll open. Oh yeah, there's a whole bunch of stuff. Why is the HTTP server stuff showing up? Oh, because it's in memory. Oh, because I opened a VI by itself. Let's reopen this project and get the hierarchy cleaned up a bit. Yeah, some of the bare VI examples that I opened up added all their dependencies helpfully to that last project. So I have gone back and forth on the design of this a couple of times. It's the reason why it took a while to get everything published that I said I'd have published at GDevCon. Because I wanted to change how the formatting was handled and clean up some of the APIs. So this has the HTTP parsing stuff. So there's a whole bunch of extra stuff in here. Instead, let's look at the TCP chat. So I kind of followed a model that's a little bit like the .NET stream API. There we go. This one has the messaging. And then just worked up from there. This is pretty similar. I mean, it's nearly identical, like class hierarchy wise, to a set of libraries I made when I was working directly for a company doing LabVIEW development. So I kind of just rehashed that, but it was you have the first abstract definitions. So actually, if I go back to the slides, there was this. So there's something that actually does the reading and writing of data. There's something that owns that, is responsible for creating that stream that data can be read and written from. And then there's an endpoint, which is responsible for creating connections. So, for instance, a server doesn't ever create streams itself. So a server is an endpoint only, but it can create clients in the form of connections that you can then get streams from and do communication. So that gave that flexibility of being able to define stuff like a TCP server, which is an endpoint, and then a TCP client can be a connection, but a connection is also an endpoint because it's got an identity, but it also has an underlying data stream that you can communicate with. So that's the pattern I went with that. I forget exactly where I got that design from. But yeah, and then things are built up from that. It's mainly me just deciding how I wanted, what bits of data and what bits of lifetime management are there, and just based on the behaviors I needed for those things, where do those lines get drawn? The stream is also the connections and endpoints are typically by reference implementation. So you can take a TCP client, branch its wire, and control it from parallel loops, interact with it from parallel loops. But streams are more a lower level setup, so they're a little bit more by value. Does the server have internal abstraction? Use this model for lower classes object endpoints. Not really. So the trick I do with the server, so if we look at a TCP server, this is probably where a state chart would come in real handy. So when a server is started, this VI is run asynchronously in the background. And all of this is doing, so at this point, the TCP listener reference has already been created. So we're gonna take that listener. And one of the tricks I'm doing with this is for reference lifetime management. Things that get created from specific TCP clients, I want them to be tied to the lifetime of that TCP client. So it then very quickly launches another asynchronous VI. So this block diagram just has an asynchronous by reference call where it actually does the wait on listener. And then this is used to for the handshaking back, whether that succeeded or failed. If it failed, that means we're shutting down the server. We can stop this loop, set some flags that it's closed down. But it does some handshaking back and forth. And then if we go in here, so all of the server implementation, there is a specific TCP server implementation. For WebSockets, there's a WebSocket server implementation. It looks almost identical to the TCP server. And at some point, I may finish abstracting the TCP server a little bit more, just so WebSockets doesn't have to do its own connection management. It can leverage this. But I did decide I was concerned in the future that, if more stuff gets added specific to WebSockets, it would cause me to pollute TCP servers with stuff that wasn't needed. So they are completely isolated. The only thing that's the same is the fact that they inherit from the same parent classes, the endpoint, connection, and stream. This is the code that actually does for TCP, does the wait on listener. If that succeeds, it then finishes setting up a new TCP client instance here. This is that handshaking back to the server loop I mentioned, and then waits for it to become invalid. It can become invalid because you called close on that TCP connection. It became invalid because you called close on the stream. You could be shutting down the server, and the server shuts down all of its connected clients, but it's just going to sit here and wait. A lot of people don't do a whole bunch of asynchronous background VIs for their connection and data communication stuff. I wanted to because nothing here is polling. That is one of the decision points I made and why things are structured the way they are, is I wanted everything to either wait forever or for a really long time. And so there's no fast polling loops. If there's no data being communicated, the system's going to sit pretty much idle. I don't know if I've actually been able to answer your question very well, but there isn't really that much. It's relatively flat implementation. Okay, awesome. But yeah, so here's TCP stuff. WebSockets would have the same corresponding members in the same exact places. They would be inheriting from endpoint, would be inheriting from connection, would be inheriting from stream. Even the serial communication does, except the serial communication doesn't have a server because you don't have a serial port that can accept multiple wires. There's a single serial bus. So the serial adheres to the same API. It's just that it doesn't have a server endpoint. It only has client endpoints. But it can work with the same messaging API. It can work with the same, anything that adheres to and uses stream data. So, for instance, that terminal emulator. I'm still hitting the wrong key. The terminal emulator I wrote just cares about the stream implementation. It doesn't care whether it's TCP or serial. Just all of the reads and writes are defined, at the parent class of the stream. And so any of the underlying types can be plugged in. You know what? I'm realizing probably the easiest way is let's look at the palette menu. So, up top is the connection. The connection, again, is what can give you a stream. So once you have a new connection, you can get the stream from it. That's where you just read and write string data. For things that support positioning, such as files, I do have a file stream wrapper, as well as an in-memory string stream, which have been pretty useful, actually. I use them a lot when I was testing my HTTP parsing. It's a lot easier to parse something that you can just create in memory instead of having to have an actual connection come in, and this is the problem with TCP. All right, well, that's a whole bunch of stuff on my computer just reset. That's 7 o'clock. That is it for me. Thanks for everybody that showed up. Thanks for the questions. Again, don't be bashful about submitting any issues to the GitHub repositories. You can find links to the specific GitHub repositories from the packages. Don't worry if you don't get the right repository because things are broken up in so many different packages. But if you're trying to do TCP, you can start with a tiny TCP. If you're looking for, a more flexible API that scales well to larger applications, definitely take a look at the streams implementations. But that is it. All right, everybody have a good rest of your GLA summit.